we've talked a little bit about statistics. We've talked a little bit about sets and counting. But now let's introduce what's essentially a good chunk of our class, and that's probability. So I would like for one of you to tell me in your own words, what is probability? Like if you hear probability, what are you thinking of? So in the chat, somebody says chance and somebody says likelihood. I like that. Let's start with the first student. What do you mean by chance? What does chance mean?
Just whether or not something could happen based on a given set of parameters.
Okay, whether or not something could happen based on a given set of parameters. I like that. I like that. I'm assuming that if you say that there are a given set of parameters, but we still don't know if something could or could not happen, that probably means that the parameters don't really constitute all of the input of whatever system you're studying. That's good. Somebody says likelihood. What do you mean by likelihood? Is it the same thing as chance, whether or not something can happen, or do you mean something else? So let's see, we say here a chance. Okay, yeah, we've said that before. Let's try with Bailey or Christian. What do either of you mean when you say likelihood?
That's a hard word to define, but I guess it's like, given the way we understand the universe, how things tend to turn out, we quantify our understanding of whether or not something is going to happen more often than not. Yeah, I think that's good.
Okay, more often than not. I like that. You know, more often than not. That's good. I'd like for you to think of these things because I always thought of probability as the chance or likelihood of something happening. But then when I get asked what is chance or likelihood, I think, well, whether something may or may not happen. But it actually, that doesn't really tell me much. You know, whether something may or may not happen, I mean, something can or can't happen. You know, if you have an experiment with multiple possible outcomes, then there's a probability for all of them. So that doesn't really define probability. But I like when you say, you know, how often they occur. Renee says it has to be governed by some kind of rules. That's absolutely right. And of course, in this class, we're going to try to figure out what those rules are. I'd like to talk about two types of probability. The first one is probably the one that we are most familiar with in terms that we hear about it all the time. And that is subjective probability, right? Subjective probability is essentially quantified as a degree of belief. So if we could somehow say how much we believe something can or can't happen, then that degree is a subjective probability. So one of the examples I wrote on the notes are, you know, I am 99% sure I turned off the oven. In fact, for some reason, every time I leave my house, I don't know if I closed the door. And I don't know, I'm never sure if I closed or did not close the garage door. So I always think, oh, did I close my garage door or did I not close my garage door? And I never lock the garage, the little door inside the garage that goes into my house. So you'll find that more often than not, I sometimes go back home and realize that I did close it and that, you know, I'm worrying over nothing. But that degree of belief, that subjective degree of belief is what we call subjective probability. You know, I'm 90% sure that this is going to happen. In fact, you may have heard, you know, when somebody says, I am 99% sure of something, that means they're not sure. Because being sure means that you are certain that something will happen or has happened or something. So if you say I'm 99% sure, that doesn't really mean anything. It means they're not sure. And that's not really what we study in this course. And when you hear subjective probability, that's actually not going to be the focus of this course. Instead, we're going to focus on something called objective probability. And that essentially is based on repeated runs of an experiment. You take an experiment, you run it again, you run it again, you run it again. If you run an experiment a large number of times, let's say 1,000, 1,000,000, a billion, well, maybe that's too much, but if you run an experiment a large number of times, if you notice that the proportion of times an outcome occurs starts to tend towards some value, that limiting value is what we call probability. I know that that doesn't mean much, so let me just give you just a quick example. If you do something like, I don't know, like, let's just do the basic example of flipping a coin, right? If you flip a coin, you may get your first attempt. Let's say you have heads or tails, and you do multiple attempts. Your first attempt, you may land on heads. The second one, you may land on heads. And let's say at the third attempt, you also land on heads. If you only focus on these 3 runs of the experiment, you might say to yourself, well, it looks like there is a 100% chance of landing on heads because I've done 3 experiments and they've all had the same outcome. But perhaps if you do one more, you land on tails, maybe another one tails, and then another one heads. At this point, you look at your results and you say, well, out of 6 trials, 4 of them landed on heads and 2 on tails, which means that I still feel that this coin is more likely to land on heads than on tails. If you keep doing it, perhaps another experiment, you're going to land on tails, perhaps another one tails again, and then another one heads. At this point, you say, well, I've done this 10 times. Or I guess 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Let's do one more. I've done this 10 times. 6 of those, my coin has landed on heads. 4 of those, my coins have landed on tails. Therefore, I believe that there's a 60% chance, a probability of 60%, that my coin will land on heads. However, if you keep doing this an infinite number of times, you'll notice that the more runs you do of this experiment, the more the number of tails and heads is going to get closer to each other. They may not be exactly the same number, but they will get so close that you'll see that the proportion of times you land on heads is going to decrease and decrease more or less until reaching a value of 50%. And the proportion of tails is going to increase more or less until you reach a value of 50%. Of course, that's assuming that all of your initial parameters are the same, the coin is very well weighted and balanced, but the idea is probability is not as simple as running an experiment 2 or 3 times and then looking at the ratio of times an outcome occurs, a proportion of times an outcome occurs. It's actually about running an experiment many, many times until your outcomes tend towards one value. There's a question in the chat that says, could you use these results to try and predict the probability of the next flip? Yes. We're not going to cover that in today's class, but we will be looking into different types of probability distributions. And one such type of probability distribution essentially focuses on looking at the probability, on using old data, previous data, to think of the probability of the next flip. With a coin, it's a little bit hard because assuming that the probability of heads and tails is 50-50, then that should, each run should be independent from the previous run. But there are other types of phenomena where you'll notice that previous results actually affect future runs of the experiment. And you'll realize, like betting on races. Yes. And you'll realize that you can actually figure out whether or not your experiment is susceptible to being altered by previous runs by just applying some simple statistical equations that we will learn over the coming weeks. So yeah, that's a very, very good question. And to answer your question, yes, and we will look into this in the future in this class. Okay. Now we're going to start with the simplest type of concept, and that is a concept of equally likely outcomes. So for example, in the case of heads or tails, if we assume that the coin is, perfectly balanced and there's the same chance of heads or tails, then we can say, well, what do you think is the chance or probability that a coin will land in heads or in tails? So in other words, if I say, what is the probability, that's P, that my outcome will be heads? Ignore these runs, just based on what you know of a coin. There are 2 outcomes. It looks like they're both equally likely. So what's the probability of the coin landing on one of these outcomes. 0.5, that's correct. 50%, correct. And also the probability of tails is 50%. Now you may realize that all we're doing here is we are counting the number of outcomes in the sample space, and then we are counting the number of outcomes in our event. And you may not realize this, but that is exactly what we are doing, because in this case, my sample space is heads and tails, and I'm looking for the probability of the event that the coin lands on heads. Now that's an event with only one outcome, or tails, that's an event with only one outcome. So what we're doing here is we're saying, how many outcomes are in the event H? Well, just one, H. And how many outcomes are in the total sample space? 1, 2. Therefore, my probability is 50%. So in the case of an experiment where you have n outcomes and all of those have the same probability, then the probability of each outcome is going to be 1 over n. So the probability of equally likely outcomes is going to be 1 over n, where n is the number of outcomes. It's a very simple concept. Of course, that doesn't really apply to everything, but at least it applies to a lot of very simple cases. Now, we've already talked about flipping a coin, and we know that landing on heads, the probability is 50%. I think that's really simple. Now let's talk about flipping a coin twice, right? If we flip a coin twice, I think we talked a little bit about this in the previous class, but if we flip a coin twice, what were my outcomes? Possible outcomes if you flip it twice? Good, good, thank you. So you have heads, heads, tails, tails, heads, tails, and tails, heads. Good, we have 4 outcomes. Now in this case, if we flip a coin twice, what is the probability that a coin will land on heads at least once? So 1 or more, once or more. 3/4, good. And notice that that's what we're doing, right? We're saying, okay, what is the probability that the coin will land on heads at least once? So what essentially we're looking for is the probability of the event that contains heads. In other words, this event has to contain heads within it. So if we count, we see we have number of outcomes in this event. Well, we have 1 outcome that has heads, 2 outcomes that have heads, 3 outcomes that have heads. So our number of outcomes in the event is 3. And then we count the total number of outcomes in our sample space. That is 1, 2, 3, 4 outcomes in my sample space. Therefore, my probability is going to be, just as you said, 75%. Correct. It's a very, very simple concept, right? The concept of equally likely outcomes, it's very simple. Now, of course, I don't mind making this class simple, but I think it's a lot more fun when we challenge ourselves a little bit. So let's look at the probability of getting a full house. So that's, if I understand correctly, that's 3 cards of 1 rank and 2 cards of another rank in poker. So for example, 3 7s, 2 5s. I don't know much about gambling. I'm a decent person, but if I understand correctly, the full house is having 3 cards of 1 rank and 2 cards of another rank. So if you're using just one standard 52 card deck and you want to draw 3 cards of 1 rank and 2 cards of another, I would like to know what is the probability of that. And let's assume that the cards are perfectly shuffled so that each card has an equally likely outcome of being selected. So this is going to take a little bit of analyzing, but right now I have 52 cards. And I want to choose 3 of one rank and 2 of another rank. And they're all equally likely to be chosen. What is the probability of this scenario? What is the probability of choosing 3 of one rank and 2 of another? Any ideas on how we can approach this? And let's start like from the very top, like in a very general concept. What am I looking for? Very generally, not numbers or anything. Just generally, what am I looking for? Oh, sorry. A rank is simply, all your 2s, your 3s, your 4s, your 5. You know that there's 4 cards of each rank, right? There's, for example, a 2 of clubs, 2 of hearts, 2 of spades, 2 of diamonds. So 2 is one rank, 3 is another rank, 4 is another rank, 5, 6, 7, 8, 9, 10. God, Jack, Queen, King, and Ace. So that's a rank.
I guess generally you could say that you are trying to pull from certain groups within the 52 cards.
Exactly, right?
Mm-hmm.
I think one good way of saying this is, well, let's just call this an event. We can call it event F, where F is an event that includes 3 of one, that pulls 3 of one rank and 2 of another. And all we're really trying to find is how many possible combinations do we have of cards that have 3 of one rank and 2 of another. So in other words, we're looking for the number of outcomes in the event that I'm just calling it F. You can call it whatever you want. This is just a variable. So I'm looking for the number of outcomes. So how many possible combinations I have, and there's a key word there, right? How many possible combinations I have of 3 of one rank and 2 of another. And I want to divide that by the total number of combinations for my 52 card deck. I'm selecting 5 cards, and out of those 5 cards, I want to know how many of those in how many ways can they be arranged to give me 3 of one rank and 2 of another. And I'm going to divide that in all of the possible ways our cards can be drawn. So if we choose the chat says, if we use the choose model, we'd want to choose 3 out of 4 and 2 out of 4. That's absolutely right? That's correct, right? And there's a key here, right? If we're talking about combinations, you know that we're going to be using the binomial coefficient, right? We're going to want to figure out how to choose a number of cards from a larger number of cards. So Renee is absolutely right. If we're using the choose model, and I know that we want to choose 3 of one rank, but how many cards in each rank? 4. We have diamonds, hearts, spades, and clubs, right? So there are 4 cards of each rank, but we want to choose 3 of them. You can think of, let's say that number is 3. There are 4 3s, and you want to choose 3 of those 3s. In other words, out of 4 cards, you're going to choose 3. So this is just 4, choose 3. However, let's think, right? How many possibilities do you have within this rank? In other words, if I'm selecting 3 as my card, then yes, there are 4 choose 3 combinations of 3. But I could also choose 4 as my card, and there are another, so this will be plus 4 choose 3 combinations of 4, 4 choose 3 combinations of 5, 6, 7, 8, 9. So how many total 4 choose 3s would we have? We'd have to add them all up, but how many would we have? How many 4 choose 3s? 13, good. That's from exactly the number of ranks. That's correct, Renee. So from 2 to 10, and then jacks, queens, kings, and aces. And that's a total of 13 ranks. So let me just make some notes here. So this is the number of ranks. And this is the number of possible combinations of 3 cards for each rank. Good. Now, 13 times 4 choose 3 is simply the number of possible combinations of choosing 3 of one rank. However, we also need to choose 2 of another rank. So in that case, if we're choosing 2 of another rank, what would be my binomial coefficient? If we're choosing 2 of a rank, so Yep, 4 choose 2, that's correct. Right, because we have 4 cards in each rank, and we want to choose 2. Now, I want to be careful here. In this case, since we've already chosen 3 for the first rank, how many ranks do we have left? 12, correct, because we already chose from 1 rank, so we can't really choose from that rank again. So now we're stuck with only 12 ranks to choose from. And of course, remember, this is like taking an experiment and dividing it into different steps. In step number 1, you choose 3 cards of 1 rank. In step number 2, you choose 2 cards of another rank. And if these are different steps in an experiment, how can we find the probability of the experiment as a whole? One of the easiest ways to count, we multiply. Correct, Samuel. Correct, we multiply. So that is the number of outcomes in F, a number of possible combinations of full houses. And now we want the number of outcomes in S. And this one we actually did last time in the last class. We have a total of 52 cards, and we know that we need to choose 5. So therefore, our number of outcomes in a sample space is 52. Choose 5. So I'll give you a minute to tell me what that probability looks like. I think in the last class, we already said that the denominator was 2,598,960. What about the numerator? What do you think the numerator looks like? If you need a refresher, n choose r is going to be n factorial over r factorial n minus r factorial. So Marcos says 3,744, and that's correct. So therefore, my probability becomes what? We know the number of outcomes in my event, so the number of possible full house combinations. We know the possible combinations in just picking 5 cards. Christian says 0.14%. Can somebody confirm that value? I don't really have it, so 0.14%, good. Good, that's correct, that's correct, thank you. And you can see it's a relatively small probability. But now, does it happen? Do people get full houses in poker? Yeah, it does happen. It's not, it's not very likely, but it does happen, right? So how do we reconcile that? Like, how do we reconcile the fact that the probability is so small, but it still occurs, you can say relatively frequently? The law of truly large numbers? Yes. Yes and no. So that is a possible reason. But you'll notice that when we are playing, it's not, the experiment doesn't work in such a way that people are just randomly drawing cards from a 52 card deck. You're playing with other people. Doesn't the probability go down when actually playing, since other people have their own hands as well, or would that increase the probability? So that's where I'm trying to get at, right? You're playing with other people, and other people are also choosing for you. And when they choose for you, you may think that the probability goes down, but actually what you're doing is you're reducing the number of outcomes in the sample space at a faster rate than you'd reduce the number of outcomes in your event. So when you choose cards, yes, you are reducing the chances of full houses, but you're also reducing the number of outcomes in the sample space. So overall, the probability increases. Now, of course, we need to analyze a little bit more, learn a little bit more probability before we start dealing into the specifics of the game. But just to keep in mind, sometimes managing or dealing with probability is not as easy as looking at a number and drawing conclusions from that number. It's like you have a higher chance, right, of let's see. I know people that are afraid of planes, right? People that are afraid of planes, they're always being told that you have a higher chance of being in a car accident than in a plane accident, right? But again, it's not just a matter of looking at numbers and then drawing conclusions from those numbers. Okay? Would you subtract 5 times the number of players from the 52 in the denominator? Well, you have to subtract the number of possible hands, but the problem is that these are combinations of hands. So once you select your hands, you're not just subtracting, you know, you're not just subtracting 5 cards or 5 possible combinations. You're actually subtracting all the possible combinations that arise from those 5 cards. So a little bit more complicated. You subtract a little bit more. And that's why this number goes down at a faster rate than this number. We can keep talking about that later. I just wanted to give you a bit of an idea of how, you know, of what an easy, not easy, but a slightly challenging probability calculation would look like. Now, all of these examples that I've talked about have something in common, and it's that they are all examples of equally likely outcomes. However, in reality, not all of our experiments are going to have equally likely outcomes. And if the probability of 2 outcomes in an experiment, if the probabilities of 2 outcomes in an experiment are unequal, we cannot apply this same procedure. If I say, what is the probability that there is life in Neptune? My sample space consists of life and no life. If we use the same procedure we used earlier, we would say, well, the probability is the number of outcomes in the event, that's 1, over the number of outcomes in the sample space, that's 2, 50%. I don't know, you can go to any astronomer or something and tell them, hey, there's actually a 50% chance that there's life in Neptune, and I can prove it to you mathematically, and they're just going to laugh you off. Because, frankly, when there are other factors that play into an outcome, then we need to consider how those factors affect the probability of each outcome. In other words, when you run an experiment multiple times, sometimes some outcomes are going to recur more than other outcomes. Okay? So when we're dealing with unequal probabilities, typically we can find those unequal probabilities through observation. And sometimes we may be able to apply some statistical tools to find the values of those unequal probabilities. So would this be where the Chinese, the chat says, would this be where the Chinese rocket example falls since there's more water than land on the planet? That's correct, right? And not only that, there's definitely different factors that are going to play into where the rocket will land, but the idea is, if you think of the whole world as a candidate, which that wasn't the case. I know there was like a big area that was selected as a possible candidate, and you look at the size of the chunks that were falling, and you compare the sizes between the chunks that are falling and then the areas where it could probably land on, it could probably crash on, then you can see that that proportion is actually really, really, really small, meaning the probability is actually really, really, really low. And then if you look at, you know, that area, most of that area is water anyway. I always see in alien invasion movies, they always go to the important monuments and cities, right? I mean, there's some logic to that. If I was an alien and I was invading a planet, I'll probably go through their most populated areas. That's probably where the economy is. That's where they run their economy. That's probably where their leaders are. I don't understand why they destroy monuments. You always see the Statue of Liberty, a Big Ben, all those being destroyed. But definitely big cities makes a little bit of sense. But if an alien was just shooting at random, just like shooting towards the Earth, and each, or the laser or whatever, was equally likely to fall on any city, then you would see that there'll be less big cities affected compared to, you know, a planned invasion. I want to watch an alien invasion movie now. What is the best alien invasion movie in your opinion?
I can't think of any.
You can't think of any?
Not off the top of my head.
Loaded question. District 9? I like District 9, but District 9 made me think. It's a movie that makes you think. I like movies where it's just ooh, death and all that stuff. You can't really count Men in Black. Men in Black is not really about alien invasion, right? Because they're kind of like just peacefully living there. Unless you're trying to throw in some rhetoric that I may disagree with. But Annihilation, I have not seen it. Independence Day, I do like Independence Day.
I agree
War of
with
the
Michael.
Worlds. Yeah, Independence Day is a really good one. The first one, the second one was garbage. War of the Worlds. I like War of the Worlds. I like the original. I like the Tom Cruise one. I like the book. Chicken Little. I guess. And somebody said Monsters versus Aliens. Okay. Well, it's okay. I was hoping one of you would come up with a name of a movie that I haven't seen or heard of before, and I would be able to watch it today after class, but it's okay. You did your best. There's a new one that just came out on Netflix, animated. Was it the Robinsons or something? The Murphys, or I don't know. Anyway, Mitchells versus the Machines. That's correct. Yeah, I have not seen it. I may try to watch it. Oh, I think it looks like Christian recommends that movie. Okay, let's go back to your education. Thank you for humoring me with this, but let's go back to your education. We've talked about probabilities of different outcomes, and I've also extinction. I'll look into that one. I have not heard about that one. We've said that we can look at the probability of an outcome by thinking of the outcome as an event, right? An event that includes that outcome. Now, of course, we did the example of the Full House where we came up with an event that had multiple outcomes, right? So just to give you an idea, if E is an event, so you know that S is the sample space, that's what we're using. E is an event, and it's an event that's within the sample space, so it's contained within the sample space, then the probability of that event is equal to the sum of all the probabilities, or sorry, to the sum of the probabilities of all of the outcomes in that event. In other words, if E is an event that has two outcomes, then the probability of E will be the probability of outcome number one plus the probability of outcome number two. Even though you may not realize it, we actually did this in the previous example. In this example, F is an event that contains 3,744 outcomes. However, because each outcome is equally likely to occur, then the probability of each outcome is 1 over n, right? 1 over 52 choose 5. And because there are 3,744 outcomes, we just add up 1 over this big number plus 1 over this big number plus all the way to 3,744. And that's why we get this big number. So we already did this here, but I'm just trying to explain it a little bit more in a more general sense, right? The probability of an event is equal to the sum of the probabilities of all the outcomes in that event. Okay, let's add some numbers into it so that we're not just here speaking abstractly. Let's say that I have 4 different outcomes. I'll just call them A, B, C, D, like little a, little b, little c, little d. And now let's say that I'm looking at the probability, and for some reason the probability of A is 0.1, so 10%. The probability of B is 30%. The probability of C is 50%. The probability of D is another 10%. But now, let me define a couple of events. I'm going to say that event A, big A, contains outcomes little a and little b. Event big B contains outcomes little b, little c, little d. And event big C contains only outcome little d. So my question is, what is the probability of each, or what are the probabilities of each of these 3 events, and how do we find them? Let's start with an easy one. What's the probability of event C? What's the probability of event big C? Yeah, 0.1%, because all we're doing is taking the probability of D, and that is the probability of the only outcome in that event, so that is the probability of the event itself. But now what about A? What's the probability of event big A? 0.4. And how do we land number? How did we land at 40%? Exactly. We added up the probability of A, that's 0.1, and the probability of B, that's 0.3, and we get 0.4. Likewise, probability of B, of event big B would be 0.3 plus 0.5 plus 0.1, or just 0.9. So 90%. It's a very simple concept. I know I know you all understand it, but it's very useful to keep this in mind. Because sometimes we're going to be switching back and forth between outcomes, events, outcomes, events, outcomes, events. We typically want to switch depending on what's easiest for us to study. And it'll be very helpful for you to keep this in mind, that the probability of an event is simply the sum of all of the probabilities of all the outcomes in that event. Now that we've learned a little bit, introduced a little bit of probability, we're going to have to talk about some of the laws of probability. So in this case, the axioms of probability. Axiom is from the Greek axioma, it just means truth. So some of the axioms of probability. These are very standard. They are taught in any probability and statistics class. They are generally accepted truths, and they're not like mathematical axioms where you can prove them or you can use them to prove theorems and stuff like that, but they don't really function like mathematical axioms. However, they are truth based on the definition of probability itself. So these are essentially self-evident truths. You don't need to do any mental gymnastics to actually land at them. So the first axiom of probability, the first axiom of probability is that the probability of a sample space is 1. Why? Because the sample space is the space that contains all possible outcomes of an experiment, which means that it doesn't matter, right? It doesn't matter what outcome occurs, since the sample space already includes it, then the outcome of an experiment will always be something contained within the sample space, which means that the probability of the sample space is equal to 1. This is actually really helpful for us, because if we know that the probability of a sample space is 1, and let's say I only gave you 3 of these events, A, B, and C, and I say the sample space consists of these 4 events, but I only have these 4 outcomes, but I only have the probabilities of 3 of those outcomes. How do we find the probability of D? Yeah, subtraction. We know that all of these are going to add up to 1. So all we need to do is figure out what's the difference between what we already have and 1, and that difference will be 1, and we'll find it. Very, very helpful. In the test, I may or may not give you a sample space with multiple outcomes, but maybe missing 1 value of probability. And I won't say anything. I won't tell you this is missing, find it. I'll just give you your outcomes, and then 1 outcome will not have a probability attached to it. It will be your job to then say, well, how do we know the probability of this outcome? Well, I just need to figure out if adding all of these, if that gives me 1. And if not, then whatever's missing should be that missing probability. Okay? So that's the first axiom of probability. The probability of a sample space is 1. Cannot be more than 1, right? There's no such thing as 101% probability. It's all the way to 100%, right? The probability of any event, this is axiom number 2, the probability of any event is always going to be a number between 0 and 1. There's no such thing as negative probability. You can't really have probability more than 1 because, again, 1 just means that it occurs, right? It's going to happen. If you think of it in binary terms, 1 is the probability of the sample space equals 1 is the event that the experiment occurs, right? And then 0 is the experiment does not occur. Therefore, there is no outcome. But there's no 2 here, right? This is a very, very binary thing. Now, the probability of an event is going to be somewhere between 0 and 1. It cannot be less than 0 because there's no such thing as negative probability. It cannot be more than 1 because, again, by definition, you cannot have more than 1 as a probability. And finally, this one is not really that self-evident. I mean, it technically is self-evident. It's just not that intuitive. But if 2 events are mutually exclusive, in other words, for mutually exclusive events, that means that they don't have any outcomes in common. And I think we talked about this last time. If 2 events are mutually exclusive, what is their intersection? So if I draw a Venn diagram, this is event A, event B, what's the intersection of these 2 events? This is A, this is B. No, right? There is none. Good. Good. The intersection is nothing. I think I see some in the chat. I think you may be confusing that with the union. The union contains everything in A and everything in B, but the intersection is everything that's in both at the same time. But if two events are mutually exclusive, then they don't have anything that overlaps. There's no overlap, and therefore their intersection is null. Okay, just an empty set. So if two events are mutually exclusive, then the probability of their unions, so let's say the probability of the union of event 1 and event 2 is simply going to equal to the sum of the probabilities of each event. Not that intuitive, but definitely self-evident, because you notice here, right? We already said that the probability of an event, right, is the sum, okay, of all the probabilities of the outcomes in that event. So all we have to do here is to just add up all the outcomes in each event if the events are mutually exclusive. Of course, that doesn't really work if there's overlap in each event, because if there's overlap, then you need to find a way to, I guess, the opposite of make up, right? Because you'll have a set of events that's overlapping, and therefore you're kind of going to count it twice. So you're going to have to subtract it from somewhere, right? If you're counting it twice. But we'll talk more about that later. So these are the three main axioms of probability. From these three, we can come up with two other, they're not really called axioms, but we can call them axioms. So these are the three main ones. But from these three, we can actually derive the following relationships. The probability of an empty set is what? Let's think. The probability of an event is the sum of the probabilities of the outcome in that event. But if the event is an empty set, it has no outcomes, then it cannot have any probability. It's just zero. Good, that's absolutely right. So the probability of the complement, what is an example of that? I really can't think of an example other than just showing you, right? If you create an event that has no, so if your event is empty, event D, right? It's just empty. There's nothing in it. I mean, you can't really add anything here. Remember, the probability of an event is the sum of the probabilities of each outcome in the event. If there's no outcome, then there's no probability. I think one way to look at that would probably be the probability of the intersection of two mutually exclusive events. We know that the probability of the intersection of two mutually exclusive events, and that's an empty set, then it's going to be zero. Renee's right. Like, what's the chance of rolling a 6 when you flip a coin? Yeah, that's correct. Or what's the chance of rolling a 7 when you flip when you roll one die? Right? 7 is not really an outcome there, so there is no outcome. So the probability is just zero. Thank you, Renee. That's a really, really good example. I'm going to remember this for future classes. Finally, well, not finally, but another truth that we can more or less derive from these axioms is that the probability of the complement of an event is simply equal to 1 minus the probability of that event. Hopefully this one becomes a bit more intuitive if you see it graphically. I'm going to divide my sample space. This box is my sample space. I divide it into two events, event A, and then everything that's not A, I can just say the complement of A. Now we know that the probability of a sample space equals 1. We also know that A and the complement of A are mutually exclusive, right? There's no overlap between them. And because there's no, by the way, this is supposed to be a prime. And because there is no overlap between them, then the probability of both of these is just the probability of A plus the probability of the complement of A. And because the sum of these two is the sample space, this should be just E. Yeah, just E. No apostrophe there. You're absolutely right there. So the probability of A plus the probability of the complement of A is simply a sample space. And we know that the probability of the sample space is 1. And from here, we can derive this, right? The probability of A prime is simply 1 minus the probability of A. Okay, that's a relatively simple derivation. Maybe graphically is a little bit nicer, but you know, the truth is still there. The truth is still evident there. And finally, we can derive kind of like a third level truth, which can also come from it. And that is if my event 1 is a subset of event 2, in other words, it's included within event number 2, then the probability of event number 1 is always going to be less than or equal to the probability of event number 2. It cannot be more. So if one event is contained within another event, let's say an event contained within a sample space, for example, then the probability of that event cannot be bigger than the probability of the event in which it is contained, right? Because the probability of an event is the sum of the probabilities of all the outcomes in the event. And if your event is contained inside another event, it cannot have more outcomes than the other event. That means the probability cannot be bigger. So these are the 6 axioms of probability, the 3 main ones, and then, you know, 3 more that we kind of derive from the main ones. And I think if you understand all these, if you can keep this list handy, it may be helpful when you are dealing with different types of events, with different sample spaces. Okay. I think we're doing really great on time. So that's a good thing. But let's keep moving on. Let's try to cover as much as we can before our first break. We've talked a little bit about events, probabilities of events, probabilities of individual outcomes. Now let's talk a little bit about these set operators that we learned about in the previous class. So I'm going to start with the probability of a union. Now, we already said that if 2 events are mutually exclusive, then the probability of the union is simply the sum of the probabilities of each event. But that's only if they're mutually exclusive. Now let's look at what happens when there is overlap between the 2 events. Now, I could just give you this equation. It's in the notes as well. But I think we can actually, you can actually come up with this equation on your own. So let's think. In this case, if I want to find the probability of the union, I'm going to call these A. And A is, by the way, A is the entire circle, the red circle. I should just written it outside. And I'm going to call this one B. B is the blue circle. Okay. What is the probability of the union of A and B? Well, we think about it. We know that if they are mutually exclusive, we're just adding up the probabilities of the outcomes in each event. So let me start there, just so that we're on the same page. Probability of A plus probability of B. What's wrong here? What am I missing here? What's wrong?
That would be the odds of all of A or all of B, like getting either one of them. We're not taking into account the intersection.
Exactly, right? There is an overlap. So what I'm doing here is I'm adding up all of this, which is good, and all of this, good. But then I'm adding to that all of this, okay. But also I'm counting this again. So I'm counting this twice. So how can I make up for that here? Since I'm already counting for it twice, what adjustment can I make to get the probability of that union?
Subtract multiplying both of them together?
Correct. Subtract, not really multiplying, but subtract the outcomes that occur in both of them. And how do we find the outcomes that occur in both of these events?
So we basically add both events minus the overlap.
Exactly, good. And the overlap, remember, is the intersection. Good. And that's it. You pretty much found this. You found this rule. The probability of a union is equal to the probability of each individual event in the union minus the probability of the intersection of both events. You can do the same thing for 3. It's a little bit, you know, we can visualize the same thing for 3. So if we add a third event, let me see if I have I should have a marker with a different color here. There we go. If we add a third event, it's called the C. And I would like to know the probability of A, or sorry, the probability of the union of A with B with C. Then what am I looking at? Well, let's start by adding them all up. We know that at least that gives us something. But here, what did we do? Well, we added them and then we already counted this twice, but now we're also counting all of this twice. And now we're also counting all of this twice. So of course, we're going to have to subtract the intersections of all of these events. So what I can do now is subtract the intersection of A and B. I can also subtract the intersection of A and C. I can also subtract the intersection of B and C. But then I have a problem here. Let's see if we can figure that out. Visually speaking, what is the problem? I subtracted these three. Okay, good. Then, but what happened here?
Did you subtract too much because even the overlaps overlap with each other?
Exactly. So these overlaps, let me see if I can pick a different color here. I should have actually prepared all my nice little colored markers here before I started, but these overlaps actually overlap with each other. So what I did was I ended up subtracting this little overlap more than what I should have, right? So now I have to add that little overlap back up because I already subtracted it. I already got rid of it. I need to add it back up. So now I need to add the probability of the intersection of A with B with C, right? The little section that overlaps with all three, with A, with B, and with C. We can do the same thing for 4 events, for 5 events, for 6 events. Now, obviously, this is going to become bigger and bigger. Oh, looks like my my internet may have cut off, and I'm reconnecting. All right, let me know when you can see my.
You just jumped for a
video.
second. We didn't really lose you.
All right, is it still back? Is the video still up?
Yes.
Looks like it's still up, yeah.
Okay, that's good. For some reason, it says here that the video is reconnecting, but if you can see it, then it should be fine. Can you see me move?
Yep.
Okay, good. All right, so we can keep doing this for 4, 5, and 6. You'll notice that this equation is going to get bigger and bigger and bigger because every time we're going to have to subtract, then we'll realize that we subtracted more than what we should have, so we need to add back up. But then we realize with 4 that we added more than what we should have, so we have to subtract again, add back up again, subtract, add. But the idea behind it, or my idea here for you, is that you can actually figure this out on your own. You don't really need to memorize this. You just have to draw it, and visually you'll notice what you're missing. Now in this class, we're not going to go. We will rarely go beyond 3, so because it's not really a how well can you do set operations class. It's a statistics class, so we probably won't do 4 or more events in this class. Okay. So that's pretty much an introduction to probability and how we find probabilities of events, how we find probabilities of unions of events, and how we deal, right, with the cases of events that have multiple outcomes. Now, probability, I wish I could say it's as simple as what we've just talked about and what we've just learned, but actually it becomes a little bit more complicated the more we study it. Thankfully, we have a whole summer semester to learn how to master and study probability. But for now, let's start with the very, very simple parts of probability. And let me make sure that this is recording. Yes, it is still recording. That's good. So I think the first subsection that I would like to talk about is that of conditional probability. Okay. And this goes into the idea of, what happens if your experiment has multiple steps, and in each step, the probability is reevaluated. In other words, the probability changes. That's the concept of conditional probability. In other words, we're saying that if one event happens or if one thing happens, then maybe the probability will be a little bit different than if something else happens. For example, you look at something like your car, I don't know, your car failing on you. Assuming that two people have the same car and they've driven it the exact same amount, the exact same distances, and they more or less give it the exact care, except that one person changes the oil and filter relatively regularly, let's say every 6 months to a year, or every 3,000 to 6,000 miles. The other person never changes its oil. Now, even though everything else is the same, maybe at a starting point, both persons have the same probability of the car failing on them. But the more time passes and the more person number one changes its car's oil and filter, and the more person number two doesn't change its car's oil and filter, those probabilities actually change, right? You'll notice that the person that takes better care of their car will have pretty much the same probability of the car not failing on them. Maybe it may get worse, but at a smaller rate, a slower rate. But the person that doesn't really take care of their car, that probability is going to increase and increase and increase. And that's what we call conditional probability. It means looking at previous events that occurred and then using those to update, right, the probability of something occurring. I wish I could say something good about myself for this, but actually it's quite the opposite. In my family, we had hand-me-downs, right? Hand-me-down clothes, hand-me-down cars. And for some reason, every time a car came into my possession, it would break down. And I always told myself, perhaps in an effort to make myself feel better, I always told myself that the reason cars will always break down within 6 months to 2 years of being handed down to me, it was probably because everybody else messed them up, and then I just got the cars messed up. But then I bought my own car, and I also messed it up. I realized it's not that. It's not the fact that I'm getting a hand-me-down car. It's actually the fact that I don't take care of my car. I'm actually not good at that. And that's the essence of conditional probability, right? If the car would be handed down to somebody else in a family, in my family, then they would actually have less of a probability of their car breaking down. Ramtin says, "You'd be a good customer for me." Ha. No, I take good care of my car now. I learned my lesson multiple times. So now I take really good care of my car. But yeah, that's the idea, right? Conditional probability just says that given some event occurring, your probability may change. And we actually write that in, let's say, mathematical form as the probability of B given A. This means the probability of B if A has already occurred. So let me just write that clarification here. If A occurred, then the probability of B is P of B given A. And there's actually a nice way of figuring this out, right? And I know that there's always an equation in the notes. I think my notes are relatively complete, but let's find out what that equation is on our own. Like I said, it's nice if you read the notes ahead of time because you'll be prepared. But even if you don't read the notes ahead of time, I think that this class can still be interesting because you can kind of come up with things on your own, and it is rewarding. I'm going to give you 2 different events. I should have used colors, but anyway, this is event A. And it's not going to be a perfect circle. Let's say this, something like this. This is event B. So A and B definitely overlap. Right now, if this were, let's say, a a very arts and crafty type of class where I give you a sheet of construction paper and you draw A and B and you draw them to perfect scale. And I tell you, give me the probability of B. That's it. That's all I'm asking you. Give me the probability of B. What could you do? This is, let's say this is all drawn to scale. I want the probability of B. And it's all drawn to scale. You have everything you need. You have measuring tape. You have everything you need to calculate any geometric properties. How can you give me the probability of B? And let's say that within the sample space, each unit area in the sample space has an equally likely outcome. So how can we find the probability of B? Exactly. Would it be a ratio of our area B to 1? Correct. You could grab the area of B, put it over the area of this. That's correct. You find the area of event number B, or event B, find that area, and then you divide it by the area of the entire construction paper, the area of the sample space. Good. But now let's look at something different. Let's say that A has already occurred. Okay. So if A occurs, then the probability of A is just, the area of A over the area of the sample space. But after A occurs, what is the probability that B will occur? Are you going to take the area of this entire B and divide it by the area of A? Or are you going to take the area of this entire B divided by the sample space? What would you do to find the probability of B after A occurs? So once A occurs, given that A occurred, then what is the probability of B? Think of it this way. Since A has already occurred, does anything outside of A matter? No, because we know that A occurs, therefore the complement of A, it doesn't matter. It has not occurred. So since A occurs, all we care about is what's inside A. Exactly, Bailey. In this case, if we want to find out the probability of B, given the probability of A, so we actually need to find the probability of this, okay? This little smudge, the little smudge of what do you call it? The little smudge of B that intersects with A. Okay? Now, of course, there's a name for that, right? What is this? The intersection of A and B. So all we're doing here is we're finding the probability of the intersection of A and B. Now, here's a problem. The probability of the intersection of A and B is like me taking this little smudge and then dividing it over the entire sample space. But that's not what I'm doing, right? I'm looking at the probability of B given that A occurred. So instead of dividing this area by the entire sample space, what do I divide it by? Because we're not dealing with the sample space, we're dealing with A, correct? So we're dividing it by the probability of A. And that's all that we're doing. If you want to think of it in terms of areas, then we have the area of the intersection of A and B. We divide it by the area of A. And of course, if we divide both of these by the area of the sample space, then all we're getting is this, the probability of the intersection of A and B over the probability of A, right? Because we already know that this divided by the sample space just gives me the probability. So my conditional probability law, or not law, a rule, the conditional probability rule tells me that the probability of B given A is equal to the probability of the intersection of A and B over the probability of A. Remember last time we said that the probability of A cap B is the same as the probability of, or sorry, last time we said that A cap B is the same as B cap A. So because that's the same, then we can also say that the probability of A cap B is the same as the probability of B cap A. And this will be important later, okay? But that is the conditional probability. And we typically say this as the probability of B given A. Conditional probability is going to be interesting because in this class, it's not just about looking at one event and seeing what happens. Sometimes we need to look at what's happening, and that will influence, right, the probability of something else occurring. Let's look at textbook example, relatively simple example. And this is an example with defective parts and surface flaws. It's not really, may not be related to all of you, but it is a nice little manufacturing example. I like this example because one of my students, former students from my fluids class, works at Yamaha Motors, and part of his work right now is coming up with ways to predict potential flaws in their equipment. And one of the predictors they are using is the noticing visible or surface flaws. In other words, they're saying if this part has a flaw on the surface, a flaw that can be visualized, that can be captured with a camera, then what is the probability that the part is defective, that's completely defective, the part doesn't work? So, you know, it may not apply directly to all of you, but it is definitely something that people do and look at. In fact, it's something one of my students is actually looking into right now for his intern. Okay, so let's suppose that you are inspecting parts, and your inspection is a two-part inspection. First, you check if your parts have surface flaws. In other words, if they have imperfections that you can see in their surface. So you look at your little clipboard and you say, okay, I want to know if they have surface flaws. Yes or no? But then a second part of your inspection is to see if the part is actually defective. In other words, does the part work or does it not work? Sometimes parts can have surface flaws, but they still work. They still complete their function. Sometimes parts don't have any surface flaws, but they still don't work. And sometimes parts have surface flaws and then they don't work. Okay? So in addition to looking at whether or not your parts have surface flaws, you would like to see if your parts are defective or functional. So you prepare your little table and you start inspecting. And you start to complete this table based on the results of your inspection. You inspect 400 materials and you find that 10 of those have surface flaws and are defective. 18 of those don't have surface flaws, but still they're defective. 30 of those have surface flaws, but they're not defective. And 342 of those don't have any surface flaws, and also they're not defective. Okay? So now I'm going to ask you a couple of questions. We have inspected 400. Yes, we have inspected 400 parts. If I place those 400 parts all in a bin, and then I pick one at random, such that each part is equally likely to get picked, my first question is, what is the probability that that part that I picked is defective? And just to give you some variables to use, let's say that D is the event that a part is already defective. So what is that probability? We say 1 over 10. And how do we get that number? I put all my 400 parts. No, that's wrong. Okay, we can try again. Around 7%. I like that you're calculating this and giving me answers, but also let's see how we get to those answers, right? Exactly. I think that's a little bit better, right? So what's the probability that it's defective? Well, we figure out how many defective parts do we have. So it's the number of outcomes in event D. So event D has 10 plus 18, 28 outcomes, right? And then we see what is the probability of the entire sample space. How many outcomes in the sample space? 400. So, oh, okay, that's fine. No problem. So we have 28 events over 400. So that gives roughly, or not roughly, I think it gives exactly 7%. I think. I'm not sure. I could be wrong. Okay, good. I think that was a relatively easy concept to get. Good. But now, what is the probability that your part is defective if it has surface flaws? And before you give me the answer, what am I looking for here? I'm saying, what is the probability that a part is defective if it has surface flaws? What am I looking for? The probability of what given what? We can call this D. Let's call this F just because S means sample space. But what am I looking for here? D given F, correct. And I'm looking for the probability that a part is defective given that it has a flaw. And again, I'm calling my surface flaws F instead of S because S is typically reserved for sample space. I don't want to confuse you there. Okay, good. That's exactly what I'm looking for, right? And if I'm looking for that, then I really want the probability of the intersection of F and D over the probability of F. So what do we have? Well, the intersection of F and D are parts that have surface flaws and are defective. That's correct. I see your answers. They're all correct. Good job. So we look at surface flaws, yes, and defective, yes. The intersection is just 10. And then we divide it by the probability of F, which is the probability of surface flaws. So surface flaws, yes, there are 40 outcomes that give me surface flaws. Now, technically, I want you to be careful, okay? Because all I'm doing here is counting the number of events, but that's not really what a probability is, right? The probability of F cap D is not just 10, okay? It's what? 10 over what? The probability of F cap D, right? The probability of this in respect to the entire sample space is 10 over what? Because I see a lot of you wrote 10 over 40. That's good. That's this over this, but exactly 10 over 400. And now the probability of surface flaws is 40 over what? Again, I'm looking at the parts as a whole. So 40 over 400, that's correct. So because those 400s cancel out, that's why I up with 10 over 40, okay, which is just 25%. Does that make sense? I don't want you to get confused because I see that everybody jumps straight to 10 over 40, and that's great. I mean, it is the right answer. But let's understand that we're not just counting outcomes, we're actually looking at probabilities. Now, in this case, because they're both divided by 400, then it cancels out. It isn't always the case, right? So let's just keep that in mind. The probability of a part being defective, given that it has surface flaws, is 10 over 40. You can look at, well, surface flaws. Then you can look at, okay, how many within surface flaws, that ratio. Then that's good. It's not going to give you a wrong answer, but I do need you to understand where this is all coming from. Before we take our break for today, let's do one more. What is the probability that a part is defective given that it does not have a surface flaw? So here I'm looking for the probability of D given what? I'm saying given that it doesn't have a surface flaw. Is there any way to express that given, using D and F as our variables? Probability that a part is defective given that it doesn't have a surface flaw. Correct. Yep. We look at the complement of F. If F means that a part has a surface flaw, then the complement of F means that a part doesn't have a surface flaw. Same thing. We find the probability of the intersection of F prime and D divided by the probability of F prime. And what is that? Probability of F prime, so no surface flaws, and D, so yes, defective. Well, we have 18 over 400. And then here, what do we have? The probability that a part does not have surface flaws, is that 342? 360, that's correct. So we are left with, right, 18 over 360. Remember, it's not just no and no, it's all of the events that don't have surface flaws, 342 and 18. Okay, so we have 18 over 360, and that's about 5%. Good. Any questions on this? All right, if there are no questions, let's take a 13-minute break and we'll meet back at 3:30.